Okay, example. A little tiny weeny example to give us the huge challenges in what I've been able to teach you so far in the course. Sort of show the limitations of those linear tools that I've given you so far. We are producing some plates, maybe insulation plates. They're a bit sort of roughly, not very precisely cut in the company. The length is on average 2 meters, but with a standard deviation of 1 centimeter. So plus minus 2-3 centimeters. The width are 3 meters on average with a double standard deviation. Now, for part of the planning, budgeting and everything, part of the computation and control of this system, we are actually interested in not the length nor the width, but in the area, and then maybe volume, but the volume is a simple function of the area. So let's start with the area. If we cannot deal with the area, the volume is a no-go. So let's go for the area. Now the area, that's the product of the length times the width. Then I ask the question, which I didn't teach you to answer. What's the mean area? What's the standard deviation from plate to plate in those areas? Yeah, I know distribution of X and no distribution of Y, but what about the distribution of the product of Y times X, X times Y? Which means any kind of events, like how often do I actually produce something which is off target by more than 0.1 square meter, say. That could be kind of a frequency we'd like to know for quality insurance or quality specification. Well, I need to know about the distribution of the product of X times Y. Well, I don't teach you in this class how to find that probability distribution. You need to take a full class on probability theory. It's a nice course, 2405, nice teacher. Please go ahead and take it. As an engineer, these are very good tools. There are a lot of important probability calculus tools and models out there. But hey, if you just want to answer this question, just listen in for 30 seconds and you're there, instead of taking a full class of probability theory, right? I'm not suggesting that has no use, but for this little problem, here are the 3 seconds and the few lines of R code needed to answer the question. And we go and do it in a sec, but let's look at the code here. I'm just setting the seed here, then you can reproduce exactly the same numbers if you try it yourself. I discussed the seed, I'll not discuss it much more. I decide on the size of my simulation exercise. Let's make it large. So start with 1,000, 10,000, and then try to make it larger until the computer gets tired. Then I simulate 1,000 lengths and 10,000 here even, widths. And then I compute 10,000 areas. And then I look at how they appear. And by looking at how they appear, I have the full story with all the precision that I need or that I have the time to wait for the computer to give me. And then I can look at what's actually the mean, what's actually the standard deviation, and also such complicated things, and here's a little R technicality. If I'm going to count or find the probability of having a deviation from 6 that is larger than 0.1, that's the question I put on my slide, I use a logical operator and I count. I take 10,000 differences between the actual area and 6. I check whether each of those are larger, and I take the absolute value, right? And then I just check, is it larger than 0.1 or not? And this logical operation will produce a vector of 10,000 trues and false. And trues or false in R are coded as 1 and 0. False, 0, true, 1. And by that, I take the mean of those 0 and 1s, which is the same as counting all the truths and dividing by n. This is just a proportion of truths, that I find by applying mean to this vector of 0 and 1s, right? So here is the proportion. 4.4% is the probability to go that far away. To answer this question, you would have needed to take a full probability class to find the distribution of the product of two random variables. That's being given to you in that course. But you need a bit of math and some exercises and some long hours in night to practice. But here it is. Are you happy now? Well, you shouldn't be. Are you not skeptical at all? Do you just take it for granted? Do you believe everything I say? Well, follow me. I'm the Messiah. Then. No, don't. Don't follow anyone who claims you should follow them. Sorry, now I get to where I shouldn't go. Please follow whoever you like to follow, of course. I couldn't interfere with whoever you want to follow. What's the problem still? I'm trying to push you here to at least point at one problem. And then we could see if we could solve it. Are we sure this is the right answer then? This is just a simulation. Do you want to add in? Only if it follows the normal. That's a good point. We make an assumption here about normality. Yes. Well, what if we at least believe that is okay? So we believe the normal is the right model. What would otherwise be an issue here, maybe? Yeah? What about the seed? Yes. Ooh, yeah, what could that mean if I used it? Now, let's go check. Let's go try. Because that's close to the point I wanted to have us think about. Let me at least go down to this number. Now I included the seed in my copy-paste here. Is it the truth? Do I get the same value each time? It appears to be the truth. Do you believe it now? This time I'm doing something. I did something similar stupid a few weeks ago without knowing it. This time I know I'm doing something stupid. The stupid thing is that to have an idea of how good an idea this is, I should try this without the seed. The question we should ask ourselves is actually a sampling kind of question, just like when we do real stats, is how dependent is this on my simulations really, right? It's just simulations. Wouldn't I get something different if I tried it again? If I do that, get something too different, my simulation is not very good, right? It doesn't tell me the truth. Well, the good thing is we can check. And that's the thing about simulations. If you're in doubt, try it again. Well, let's try it again. Look at the number, 504446. It's not completely the truth, the first number the truth, but it appears to be in the neighborhood, right? The truth should be around 4 to 5%-ish. Well, let's go to a mill. 45, 459, 454, 454, 456, 453, 452. I'm pretty sure it's 45-ish, right? If I operationalize this investigation, I could, if my computer is fresh enough, I could get the precision I want, right? I could get it with 2 decimal points, knowing that these are the right ones. Now, I don't teach you all the formalities of being really precise on the simulations. I'm just telling you generally, if you're in doubt whether your simulations are okay, you just try again. And if they get more or less the same, they're okay, right? That's as far as we take it. We don't go to the next meta level here. That's the magic of simulations. Whoa. It says N,000 there. That's the only thing you don't see. Capital N is 1,000. You need to be fast and have good eyes to win this contest. That was difficult to see, of course. I was taking the standard normal and then I was squaring it. And that is exactly what I say in the red. It's a distribution of the squared of a standard normal. That's what simulations can do for us. We can find complicated distributions of nonlinear transformations of something. If we know the original distribution, assuming the original, we can see what the actual distribution of some complicated computation becomes. And then a little detail that I didn't expect you to know, but if you did, you got the point anyway, that this actually becomes the chi-square distribution when you square a standard normal. That's not syllabus, but you could have heard it if you checked around. Good, I'm not gonna dance anyway.